two actually terms here we never discussed before. One is called the apparent power, and the other one is the power factor. So these are new to us. This is your first time seeing them. Now, if you remember, if you have a voltage source of a value of V maximum cosine WT plus, well, I call it theta V, because my theta and phi, I'll forget which one is which. And you put that across an impedance. So if you have this voltage source going across Z, some impedance here, well, that's going to create a current going through this load here, or this impedance.
What's the first character in your equation?
Here?
Yeah.
V.
Okay.
Yeah, just lowercase v because it's time domain. There'll be some current, which is some I sub max, some maximum value, cosine. W doesn't change, but the angle will be different. We'll call it theta I. Now, if you remember when we did the average power, P average, we called what? 1/2 V max, I sub max, cosine theta V minus theta I. Or, if you want to write that in terms of V effective, if you remember, for sine and cosine, if you remember for sine, cosine, V effective, let me just write it on a separate line. The RMS, or the effective value, whatever you want to call it. We did this one. We found that if you have a cosine function, then the V effective for it is going to be the V max over the square root of 2. And also the I effective, we did the derivation, it's I sub max over the square root of 2. So if you take V effective times I effective, what are you going to have? You're going to have V max over the square root of 2 times I sub max over the square root of 2. And if you do the math, what is that equal to? Isn't that 1/2 V max I sub max? Which means this equation now, the average power, if you don't want to use the maximum value, you can rewrite that as P average equals V effective, I effective, cosine theta V minus theta I. Now, what's the apparent power? So let's talk about apparent power. Maybe I'll do the next slide. This is your apparent power. And that's really when there is no phase shift, when your load is purely resistive. The difference between theta V and theta I becomes what? 0. What's cosine of 0? 1. So this will disappear. So ideally, that's what you like to have. You like to have your house there is no difference in theta V minus theta I. That means you're getting everything the company is sending to you. Your average power is going to be the maximum value. V effective times I effective. There is no difference in the two voltages here. So that's what the apparent power is. Apparent power is equal to V effective times I effective.
Which is still equal to 1/2 V max I max.
Correct. Yep. And the units for that, the units, because when you're looking at the number, sometimes you're not sure if that's average power, apparent power. The units is volts, ampere. Or VA. Volts, ampere. Oh, I have an extra I there. I don't know why I have an extra I. I wrote it wrong here. Volt ampere, which is VA. So that's how you know the value is actually, it's apparent power or average power. The average power in watts. The unit for this is watts. The units for this is VA. Now, what's the other term? It's a power factor. The power factor is equal to cosine theta V minus theta I. That's the other term. What percent of that power are you getting? Ideally, you want the power factor to be 1. You want to get everything the power company sends you, if that was your house. You're not going to get that. If you're getting 90%, that's good. Power factor 0.9. If you're getting 40%, that's not good. The power factor is 0.4. You know? And the power factor is either going to be leading or lagging. Now, the power factor is actually the relationship. Oh, I'll get it. And is the power factor leading or lagging? Let me write something. Eli, the Iceman. Electrical engineers use that. Now, a couple of things about that. If your load purely, that means there's no impedance there, it's all resistor. A purely reactive load, only resistors. And what is that? That is one contain, oh, purely reactive, I'm sorry. Purely reactive, not resistive. One contain, or containing, we'll say, no resistance. So what do you think that's going to be? No resistance, either a capacitor or inductor, purely reactive. There's no resistors. I mean, a capacitor or inductor. If it's a capacitor or inductor, what is theta V minus theta I? Well, greater than 0. By how much greater than 0, David? Either plus 90 degrees or minus 90 degrees. You know? Somewhere between these numbers. So they'll have a theta V minus theta I somewhere between negative 90 degrees to positive 90 degrees, somewhere in that range. And that was going to tell us if the power factor is leading or lagging. So the term leading we say leading power factor. We use the word leading and lagging power factor, or lagging power factor. You're going to see the word leading or lagging written multiple times. Leading or lagging power factor, it really refers to, it's referring to the phase of the current with respect to the voltage. With respect to the voltage. Now, here's what I'm going to write. An inductor will have a lagging power factor. So the inductance load, so how am I going to remember that? I'll show you. The inductance load will have a lagging power factor. And the capacitive load will have what? A leading power factor. I wrote this phrase up here, Eli the Iceman. I didn't tell you anything about it. L for inductor. And C for what? Capacitor. Notice the inductor here. E is actually the voltage here. The power factor, let me go back here, referring to the phase of the current with respect to the voltage. The current. Let's look at the current. Is the current written before or after the voltage? In L here. After. So that means that's lagging. It's after. There's a capacitor. Look at the current, look at the voltage. Is the current written before or after the voltage? Before. That's a leading power factor. So Eli the Iceman tells you in the inductor, the current lags the voltage. In the capacitor or capacitive load here, the current leads the voltage. All electrical engineers go by that, Eli the Iceman. You'll hear that again, again, and again. That tells you who's leading, who's lagging. In the inductor, L is the inductor, the current lags, lag in power factor. In the capacitor, the current leads. Okay, let's take an example. Well, I'll just take this example. Let's see. By the way, just going back to that equation right here. If I go back to this equation, if I don't want to write cosine theta v minus theta I can write what? What was that term? That's the power factor. So a lot of times you'll see me write that equation. P average equals V effective, I effective, times the power factor. because cosine theta V minus theta I is power factor. Just heads up there. Let me take an example here. We have a voltage source, has a value of 60 angle 0. Now notice I'm going to write RMS. I've been saying effective, or RMS is the same thing. Going through an impedance here of 2 minus 1J. Going through another impedance of 1 plus 5J. Calculate the average power. Calculate the average power delivered to each of the two loads. And while we add it, let's also calculate the apparent power supplied by the source. Let's do both of these. And while we add it, let's calculate what? The power factor of the combined loads. Calculate the power factor of the combined loads. If you take the two loads together and combine them, what's the power factor? So 3 questions I'm asking. There's question number 1, there's question number 2, and there's question number 3. Now, I can do it multiple ways. I can find the current going through that, I. I can also find the voltage across each one of these and apply the rule, right? Well, let's call this V1, and let's call this V2. If I know the current V1, V2, I'm done. I can tell you the power, average power absorbed by each one of these loads. I can tell you, if I know the current, how much power supplied by this. So let's see what happens. First question, calculate the average power delivered to each of the two loads. Let me find what the current is. And let's get the calculator ready. The current I is equal the voltage 60 angle 0 divided by what? The equivalent value. The equivalent is what? 3 plus 4J when you add them? 3 plus 4J. Is it 12 angle negative 53.1? Try that. I get 12 angle negative 53.1 if you can see it. So that's the current. Can I find V1? I can do it without finding, but I'll find V1. It's voltage division. 60 angle 0 times that impedance, 2 minus 1j over the sum of them, which is 3 plus 4j. (60 angle 0) times 2 comma negative 1 divided by 3 comma 4. I came up with 26.8 angle negative 79.7. Anyone get that number? Let's calculate V2. Voltage division again. V2 equals 60 angle 0 times 1 plus 5j over, was it 3 plus 4j? (60 angle 0) times 1 comma 5 divided by 3 comma 4. And I came up with 61 here. One comma 5, 3 comma 4. Yep. 61.2 angle 25.6. Again, do we have a confirmation on that number? So now I can tell you the average power, P average, by the first load by the 2 minus 1j. Since these are RMS, these numbers also RMS. Everything is RMS because that's the RMS value. So all these numbers that you see here are RMS or effective value. So the average power through the first one is VRMS, IRMS, or effective, times cosine theta V minus theta I. The voltage for the first one, the RMS value, the VRMS is 26.8. IRMS 12. Talking about this load, V1. Cosine theta V. What was theta V for that? Negative 79.7 minus, what was that number? Negative, that makes a plus 53.1. (26.8) times 12 times cosine negative 79.7 plus 53.1 close parentheses. I came up with 287.6 watts. That's an average power. Roughly 288 watts. Now, what's the average power for the second one, the 1 plus 5j? Again, it's VRMS, IRMS, cosine theta V minus theta I. V, that's the second voltage, 61.2. IRMS 12. Cosine theta V, which is 25.6, minus theta I. So minus to minus, that makes it a plus 53.1. $61.2 times 12 times cosine 25.6 plus 53.1, close parentheses. I got 143.9 watts. Roughly 144. So we answer the first question. Calculate the average power delivered to each of the two loads. This is the first answer. That's the first load. Top load. And this is the lower or the bottom load. The side one. That's how much average power delivered to each one of them.
Wait, so the RMS value is the same thing as the effective?
Yeah, exactly the same thing, yeah.
So like the effective values you've been doing, like they've been like constants? But
Correct.
so this one's a little bit different, that they're not constants?
What do you mean?
Oh, they've been.
You might? Okay. By the way, I could have avoided finding the voltages here, just for haha. I could have found, instead of VRMS, IRMS, cosine theta V minus theta I could figure out, because this has, when you look at this, has a resistor and a capacitor, right? We know the average power by the capacitor absorbed. How do you know it's a capacitor, by the way? I made the assumption it's capacitor. How did I know by looking at this it's a resistor and a capacitor? Negative J. We know the average power absorbed by a capacitor or an inductor is always what? Zero. So I can just drop this piece and calculate the average power through the resistor. So I could actually found that by taking, watch this, I could have done it by doing I effective squared, I squared times R. If I did that, I'd end up with that answer. What was my current? 12, right? So 12 squared is what? 144. 144 times the resistor, which is what? 2. So this will be 12 squared times 2, which is what? 288. Is that what we got? Yep. I could have got it here too. This is a resistor and an inductor. The average power absorbed by the inductor is 0. So only the resistor, 1. I could have done this I effective squared times R, which is 12 squared times 1, which is what? 144. Is that the same answer as this? Yep.
Which one's more accurate?
Yeah, the same thing. Well, that's actually no rounding here. This is with the rounding. That's why the number is actually just a hair off. It's just rounding. If you carry all the decimal places and everything will be fine. Okay. Just heads up, just in case sometimes you see us doing it that way. Now, the second question, calculate the apparent power supplied by the source. Now, the apparent power by the source, that's this guy. So I'm going to write that P, A, P, P, E, R. That's apparent power. By the source. How much power is the source supplying? The definition of apparent power is VRMS, IRMS. That's it. There's no cosine theta V minus theta I. So for this example, the voltage for the source is what? 60. And the current by the source, which is what? 12. That's the same current. So what do we have? 720. And what are the units for apparent power? VA. Now let's look at that, the last question, which is what? That power factor for the whole load. If you make this one load,
Yeah. Right?
And divide by.
yep. If you make that one load, this is what our circuit looks like. And the value of that is what? 3 plus 4J. The current doesn't change. I is still the same. I is still.
You move it up a little bit.
Yep. What's I here? We calculated I early. What was 12 angle negative 53.1, right? And what's the voltage cross that? Isn't that 60 angle 0? In parallel. Well, what's the power factor? Isn't that cosine theta V minus theta I? Which is cosine 0 plus 53.1 plus cosine 53.1 cosine, where's the cosine? Where'd you cosine 53.1 0.6. So you're only getting 60% of the power to the load. That's all you're getting. You're paying for 100%, you're getting 60%. Now, if I ask you the question, is that lagging or leading? What do you think? Lagging or leading?
Well, the current is before. Oh wait, voltage is before the current.
Let me write this. Eli, the Iceman. Eli, the Iceman. This is the inductor. In the inductor, the current lags the voltage. This is the capacitor. In the capacitor, the current leads the voltage. Well, let's look and see what you have. 3 plus 4J.
4J means you have a total of.
You have an inductor.
So
So that's a lagging power factor. Also, another way of looking at it, if this angle is positive, that's a lagging. If it's negative, that's a leading. So if you want to go back to lagging and leading, when we discuss lagging and leading, here we go. You can add to that list we said lagging versus leading. Lagging, that means theta between 0 and 90 degrees. Could equal to 90 degrees. And leading is what? Between negative 90 and 0. So that's theta V minus theta I. The difference between them, if it's a negative angle, that's a leading. If it's a positive angle, that's a lagging. If it's 0, it's neither. Purely resistive. Power factor of 1. Maybe I'll put that in my notes here. Theta V minus theta I between negative 90 and 0. It is leading. And theta V minus theta I between 0 and 90, that's lagging.
You could also calculate the average power across the combined load, couldn't you?
Sure. It's, you know the voltage of the current, if you want to calculate the average power. The question, can I calculate the average power across the combined load? Sure. You mean taken by,
Well,
so we know what the current, we know what the voltage, right? So what's the average power for the combined load? It's Vmax or RMS, not max, I'll use RMS. IRMS cosine theta V minus theta I. VRMS is 60. IRMS is what? 12. Cosine. What was theta V minus theta I? Theta V is 0. Minus a minus, that's plus 53.4. 60 times 12 times 0.6. Oh, I forgot to turn on. There we go. 60 times 12 times 0.6. 432. By the way,
or 12 squared times 3.
or take the average power from the first one plus the average power from the second one. We already calculated them individually, right? We know this is 288, this is 144. What's 288 plus 144? Better be the same answer. Anyway, we do it. The answer doesn't change. I could have went I squared times R. You're right. And I is 1, where's the combined? 3? 3 for the combined. The current's 12. 12 squared times 3. 12 squared times 3, 432. Anyway, you do it. You can take the two average powers from before, add them. You can combine the circuit, find this, or I squared times R. All of them will give you the same result.